Well, hello, everybody. Tonight, we're working on related rates problems in calculus. Sometimes, when you say related rates, when people ask you what you're studying in calculus, the person who you're talking to might start to shake and cringe. And that's okay. But you won't do that because you're going to understand that related rates problems are really just a combination of implicit differentiation and the chain rule. And really, you've got your 5 steps. Do you remember the 5 steps? Let's take a look. 1, we're going to read and understand the problem. If you don't know what's going on in the story, don't even bother. Okay? Read and understand the problem. And what you're going to find out is that the context of these problems really isn't all that complicated. It's usually water coming in or water going out, air coming in or air going out, 2 cars driving away, and we're measuring the distance between them. I mean, these problems all sound the same after a little while. Step 2, draw and label a picture. And find blank when blank. This is my little key to solving these related rates problems. Find blank when blank. Remember how related rates work. We've got action, 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 freeze! And then we measure stuff while we're frozen, right? So we're going to stop the action. That's the when. And then the find is what we're asking you to find. And the other secret is, it's all in the context of the problem. As your physics teacher will tell you, let the units tell you what to do. We'll see that in just a second. Come up with the equation, differentiate, then substitute. I cannot stress the importance of that step. You do not want to prematurely evaluate these problems. Differentiate, then substitute, and then finally solve an answer. Read the question. What is it asking you for? Make sure that you answer the question properly. If I'm telling you how fast is the marker falling, you can answer that with a negative. But if I say how fast is the marker falling down, I need you to answer it with a positive. Do your thinking. Okay, let's take a look at an example today. And what I'd like to do is have you pause the video, try this problem on your own, and then replay the video and see if your solution is similar to mine. It won't be as good, but it might be similar. So here we go. You can pause the video now. And we're back. Okay, so let's read and see if we can understand this problem. The container's in the form of a right circular cone, vertex down, with radius 4, height 16. Water's poured into the container, 16 meters cubed per minute. How fast is the water level rising when the water's 8 meters deep? I think I understand the situation. We've got a cone. That could be a little bit drawn a little bit better, couldn't it? Okay, now, what do we know about the cone? The radius is 4 and the height is 16. And as you remember from geometry class, I know we try to forget 9th grade, but if you remember, that R to H ratio will be the same throughout the cone. All right, what do we know? Water's poured into the container at 16 meters cubed per minute. That looks like a rate. A rate would be a derivative. What is a derivative of? Oh, wait, meters cubed. What dimension is that? That's right, volume. So dV dt is 16 meters cubed per minute. And that's water going in. Now, what happens when you pour water into the cone? The water level rises. And sure enough, we want to know How fast is the water level rising when the water is 8 meters deep? Find what when what? Well, I know when the water is 8 meters deep. What would that be? That would be H. And we want to find the water level. That would be water level rising. That's a change. That's right. dH dt. Now, finally, is there a relationship for this picture? I know, back to 9th grade again. Sorry. V equals 1/3 pi r squared h. Now, let's just pause for a second because that's the heavy lifting. We're basically done here. And it's just now doing the grunt work, right? The stuff we did last chapter, just taking the derivative. This is, I think, the hardest part, coming up with this. But we have to do one little thinking here. When you take this derivative with respect to t, we're probably going to have a little product rule there, aren't we, with the r squared and the h? So what we want you to do is think about this and think of a relationship, a way to get rid of the r. So let's see, can we get rid of that r? Well, I know that the original r was 4 and the height was 16, and that's actually going to be true all the way through here. So, that must mean that r is 1/4 h. So let's rewrite this equation so I'm only dealing with h. V equals 1/3 pi, and then I'm going to replace the r with 1/4 h squared h. So now I'm only dealing with h. I've got to find the h dt. I know h is 8. Oh, I think I can do this. I mean, I also know that r is going to be 2 when h is 8, but I don't know anything about the r dt. That's why I have to make this substitution. Okay, so now we're ready to differentiate, substitute, and get the answer. Let's bring it home. Okay, first, we'll rewrite v. Let's see, 1/3 pi, that's going to be 1/16. So how about pi over 48? Is that correct? I think it is. H cubed. All right, let's go. Differentiate with what? With respect to t. And are either of those variables t? No. So you guessed it, implicit differentiation. So here we go. The derivative of v with respect to t is dv dt. 3 pi over 48 h squared dh dt. You're going to get good at this after a while, I promise. Now, I can reduce that, of course, to pi over 16. But now, since I've differentiated, I can substitute. Here we go. dv dt. Now, I'm going to leave the units in because there's always physics teachers wandering the halls. And I do not want them to walk by and see us doing a problem without units. This is also a good way to make sure we check our work, right? Because what should the units of my answer be if I want to find a dH dt? I'll let you think about that. 2, 3, 4, 5. That's right, meters per minute. Okay, so this is pi over 16, 8 meters squared dH dt. Now, if I take a meters cubed per minute and I divide it by a meters squared, I'm going to get meters per minute, and that's what I want. It always works out that way. All right, let's go. So we've got 16 meters cubed per minute equals, let's see, pi 64, 16, 4 pi meters squared dH dt. So Meters squared divided by meter cubed, that's meters per minute. 16 over 4 pi, that's 4 over pi. dH, dt, go home. There's your answer. Okay? Pay attention to those units. Make the physics teachers happy. We love them. They're a little weird. Socks and sandals, I still don't understand it. But hey, we'll let it go. Units, answer, picture. Let's see. Read and understand. Did we do that? Yes, we did. Draw and label. Did we do that? Yes, we did. Find blank when blank? Yes, we did. Equation. A little bit of work, but we end up here. Here's the big one now, right, kids? Differentiate, then substitute. Boom, boom. You're done. Have a great day. Love those related rates problems.